Okay, so this is where we left off with last week. So one of the things that we had mentioned towards the end of last week is that alkanes are highly stable, unlike that of their alkenes counterparts. Okay? With that being said, the reason for that has something to do with, I can't remember where that was. Should say something about pi bonds here. Here we go, right here. Okay. Um, so, do you have to have a catalyst for alkenes? Yes, yes, you do. Alkenes do not because of these weak pi bonds, and there's going to be one exception to that, and that's when we get to the aromatics, but we're not quite that far yet. So we begin with where we left off with talking about different types of reagents, and that's how this pertains to addition reactions. And that should be hydrogenation, not halogenation. And we'll make sense of that here in a few moments. So first day of homecoming week. Oh. Now, the reason I say that should be catalytic hydrogenation is because when you look at this, what are we actually adding? Okay, we're actually adding hydrogen. So when you look at this, there is halogenation too, but not in this case. We want to say hydrogenation. Okay, and then this is also an exception to the rule here when you're going through this hydrogenation. And again, we'll show you some examples of that before the end of the day. So, without any further context, what could you presume, what might asymmetrical or asymmetric mean to you? Like, for instance, if we said someone's got symmetrical features, what might that mean? Say that again? Yeah, it would be balanced, okay? The one side of whether it's the hand, arm, or legs, or one side of the body to the other, means it's symmetrical. So then, if it's asymmetrical, then it would be just the opposite. And we gave a brief example of that maybe last Thursday or Friday. I can't remember which it was, because it's going to be important to recognize asymmetric reagents and asymmetrical compounds. Okay. So I want to do this one and that one, and then that'll be it for today, along with some examples. So when you're writing this down, when you see this process taking place in the reactions, it'll make more sense. It's very much like looking in a rule book, for instance, and describing what into the net is. You know what into the net is. You touch the net. Well, probably in a rule book, it might say any part of the hand, torso. What might it say in a rule book when the call is made into the net? Would it just say any body part, or would it say maybe any part of the hand, torso?
I'd say it'd say any body part.
Okay, and that's what would make sense to me. I really don't know. So then, when you actually, of course, see that take place in a game, maybe you're watching the JV, or you're actually officiating. You're up on the ladder, or what do you call it? Up official, down official? Is that what it is, or what? Okay. Which one do you prefer doing when it's junior high? You like being on the floor then?
I like being the upper.
Okay. You into the net. So you make the call. They look. I didn't touch the net.
Yeah, they always do.
So maybe you're wrong.
No, I see with my own eyes.
I'm just laughing how quick. Well, they always say that.
They do. They always complain. Every 20 minutes. Whether you, even if they want to judge you, call it 86%. Which I get we do that too, but
Okay. Well, does it? Maybe not so much volleyball. We talk about that with basketball. Do you appreciate officiating more when you have to do it, and then you think, "Oh gosh, now I blew the whistle. Now I got to make a call." The first thing you do is just, okay, this is what I saw, and maybe you do a quick flashback in your mind. Maybe you do. Maybe you don't. But of course, there's no chance you're going to make everybody happy. That's the first thing you'd have to tell yourself. Then finally for today, we'll wrap this up, and we won't really pertain too much of that today. We just want to write down what it is. Yeah, well, construction under, I'd say now it's getting more serious. The parking lot's now, I suppose you could say, officially blocked off. Yes, their vehicles can come in and out, but that's to be expected. So then at first glance, what would you presume that might mean? Hydration. Just say, oh, I think I know what that is. And you could go the other direction and say, well, I know what dehydration means. What might occur when dehydration takes place? You're losing something. Yes, you're losing water. So then if dehydrating is losing water, well then what might hydration be? And you're probably doing that right now. Inside of there, inside of purple Stanley, I don't know, turquoise Stanley,
Simply modern, actually.
modern?
It's called Simply Modern. It's the-
Simply modern, okay, all right.
Yep. Yep. Yep.
Okay, so we want to just put some examples up here on the board, and then that'll be it for today. Gesundheit. Okay, so let's go ahead and begin with the first type of reaction. Okay, and okay, this was that catalytic, it said halogenation, but I think it should say catalytic hydrogenation, because look at what we are adding. So we've got 2-butene reacting with hydrogen, but here again, when you wrote that down, there's something very specific about that in the parentheses for, again, it says catalytic halogenation, but it should say hydrogenation. Something about this arrow. What might that be? For the most part, alkenes do not need a catalyst. For some reason,
Are you saying two bonds get broken? Right, will only take place if these metals are present as the name implies they are catalysts?
right, so you have to have a catalyst here. Just like their alkane counterparts, I think it said something like nickel was one, platinum was another, okay? So that means you're adding some sort of metal in there, and then this is actually called a type of reduction reaction, and that's more common when we get to, I gotta think about this. Is it ketones get reduced back to alcohols, but that's quite a ways down the road. So now, of course, we have this. We got 2 hydrogen atoms. And then what would you guess, and that's not important for this reaction, but if we did this here, to where we're looking on both sides, because we're talking about being, whether something asymmetrical or having symmetrical features, what would you guess? Is this a type of symmetrical compound or asymmetrical? Yeah, it's symmetrical. And it's not going to be the reason that you think, okay? You would say 2 carbons on each side, that would be correct, but later down the road, we're going to find out that it all depends upon where that double bond is. We've got our catalyst. So one of the things that I think helps students is if you choose to do this, this is fine, and for some people, it may confuse them. We know that these dashes are bonded to these carbons because they're hydrogens. But in the past, typically we do something like this, okay? It's not showing that there's a bond there, but it's just showing that there's an availability to have a bond there. So now this proceeds because we have our catalyst now, so we see there's two openings here. This all gets consumed. So this 2-butene then must turn to what would you guess? So we've got that and we've got that. Well, what might happen to this double bond? It's going to become a single bond. That breaks. So then we have these two hydrogens here. So that means that there's one there. And then sometimes we just do this just so you know that these, whatever shapes these are, eggs or not parabolas, but with ovals? Yeah. That these ovals is where hydrogens are actually attaching.
But that can only happen if there's an important flat.
That can only happen if this has a catalyst. Okay? Alkenes are highly, highly unstable, but there's some exceptions to that. One, we said the aromatics. Two, it's not that this is really unstable, it's just what it's reacting with that you have to have those catalysts. Okay? Because if you don't see anything here, then just like last chapter, you would have put that on the other side, just no reaction. Okay? So then the next thing that we would like to do is in our types of reactions, we're going to do, and I think it's important to maybe just do something fairly similar because we're in familiar territory here. So now, from last week, what other symmetrical reagents might there be? And I didn't tell you had to write them down. I just want to know if you can possibly remember. Because when you look at this, remember on each side of the bond you have a hydrogen atom. So would you consider this symmetrical then? Did I hear no or I hear yes? Yes. So then we can do not hydrogenation, halogenation, which means you're probably picking what? Any halogen. So then probably the most common one that people would pick would be this, and I think maybe it's a little more appropriate that we'll go ahead and do this. So we've got Cl2 or chlorine. But then this is not an exception to the rule like this one is. Okay? So what we see happening is this reaction proceeds even without a catalyst because, again, alkenes are highly, highly unstable. So you could do the same thing, and that is this, and then this. So these ovals are just showing where there's an availability for atoms to bond. So then this reaction then proceeds. And I think I had this color. Okay. All these atoms are still here. So it's going to be very similar to this, except for we're not putting hydrogens on here. We're putting what instead? Right. So now you would have to write these on here because it's not just hydrogens attaching, it's chlorines.
Wait, so how do you know it's a no reaction?
Because anything like this is going to react unless it's this. This has to have a catalyst. Hydrogen and aromatics, but we're not to the aromatics yet. This is the only one that needs a catalyst.
So what would be one that's not a reaction?
Well, a no reaction would be that. There's no catalyst there.
Only like no reaction with hydrogen.
Correct.
Oh.
Yep. Okay, then the last thing I want to do, this isn't quite Markovnikov's rule. We'll apply that at a later time. I just want you to see the difference between these reagents. So we're going to go ahead and start with, and we could continue to just use this same pattern here. I bet you that doesn't show up very well. Start over. Okay. Because this is going to take some practice here. Don't think that we're going to pick this up on the very first day. Okay. Then if this is okay, that's where you have to be careful when you're talking with each other. Because if this is asymmetrical, okay, when we say that, okay, not this. Okay, does that make sense? This is the letter A, then symmetrical, because it's same on the both sides. Because if we want an asymmetrical reagent, we're talking about water, it could be one of them. It could be a hydrogen and a halogen. So then, again, you really got to be careful when you're conversing about this. Because I try to catch myself before I say this. Because, again, I could say, what is a symmetrical reagent? Well, are you talking about this? Or are you talking about one that's the same on both sides? A space symmetrical reagent. Does that make sense? Okay. So now, what is an example of an asymmetrical reagent then? Because if this is symmetrical where it's the same on both sides, what might be something that's not the same on both sides?
H and then CL.
Yeah, you could do this one. You could do this one. Not going to do the same thing, just like you said, H and Cl. You could also do that one, and then this is also an asymmetrical reagent. But you had mentioned HCl first. So then we'll make that one in blue. And I suppose we could make this one in black. Because we're not quite to Markovnikov's rule yet, okay? Because this is still a space symmetrical compound, okay? It's when this gets moved to the end, then it's asymmetrical, okay? But anytime it's not on the end, even if you had 5 more carbons on this side, it's still considered a space symmetrical. Even though you can say, well, we got 7 on this side and only 2 on this side. Right. But because of where that double bond is, it's only asymmetrical when it's on this first carbon. Okay? And there again, that's something that you probably won't pick up on until we actually apply it. But, okay, we're not reacting hydrogen. This will proceed even without a catalyst. So just like our prior examples, you could show where bonding can take place. So then, let's see, we need red, and we need blue, and we need black. So therefore, this reaction then proceeds. Here's our red ones. These are all still there. Okay. So then what happens is this double bond, just like it has in the last 2 reactions. It's going to break. Okay. So we see there's availability for bonding to take place here and here. So you can even go in that order, or you can flip-flop them. It doesn't matter. Okay. So on the second carbon, what do you want, Cl or H? You want H on the second one, so that is blue. Then on the third one, you put your Cl on. Okay? Because this gets to be a little more tricky. Because remember from last chapter, if you had this is why we wanted you to practice this. Okay? We have butane. We're going to add some chlorine to it. Okay? Right now it's no reaction, so we're going to add some heat to it. Now we've got a catalyst. How many products did we want you to account for? 2 of them. Okay? That's not the case here. Okay? And it's all because of where this chlorine is going to bond on here. That is the issue, because here, these 2 atoms can flip-flop. Okay? Even if they do that, would you have the same compound then? Well, let's look. What happens if we do carbon to carbon to carbon to carbon? We had bonding available here and here. So we said hydrogen on the second one. But now we're going to put it on the third one, going from left to right. Then we'll put the Cl up there. What do we notice about these 2 compounds, perhaps? They're the same thing. But that's not what happens here. Because from last chapter, where would one of these chlorines attach to? The first one and the second one. You didn't have to label them. But here, if we had another carbon in the parent chain, well then, yes, you would probably have to write 2 reactants. But because of this, they're the same thing. So it might be a little confusing. It's going to take some time. Don't think, my gosh, I really don't know what we're doing. Okay? Just be patient, and we'll continue to work through this. Okay. Barring no questions, we will call this a day. All right, we'll catch up to you next time.